In this video, we're going to derive the formula for the distance from a point to a plane. So this is an arbitrary plane, and we're assuming that the equation that represents the plane is ax plus by plus cz is equal to d. This is a linear equation in 3 dimensions. And when we have the equation of a plane, we get for free the normal vector, or a normal vector, that is perpendicular to the plane. And again, that is going to be the coefficients on x, y, and z are the components of a normal vector that is perpendicular to the plane. So that normal vector can be graphed initiating from any point in the plane. So let's assume that this is our normal vector ABC. Now let's consider an ordered triple P1, which is x1, y1, and z1, and we're wanting to find the distance between this point and the plane. And the closest distance between the point and the plane is going to be such that it drops perpendicular to the plane. So the closest distance from a point to a plane is going to be the measure of the line segment that's perpendicular to the plane, getting me down to it. So let's consider another arbitrary point in the plane somewhere. We'll call this some initial point in the plane. P naught is equal to x naught, y naught, z naught. And let's consider the line segment, or actually let's think about this as a vector that is going to initiate from P naught and terminate at P1. And let's let this vector be called vector b. Remember that we do need to put vector hats on top of everything that is a vector. So vector b is going to be the vector from p naught to p1, and that vector is going to be determined by, or will have components that are terminal minus initial. So let's think x1 is the terminal x value minus the initial x value. That's my x component. The y component will be terminal minus initial for the y values, and the z component as well is terminal minus initial to get the change in the direction of z. Now, since we can move our vector n to any point on the plane, let's move it to where it is initiating at this same point, which is the closest point to P1, and that it's going in the same direction as that line segment whose distance we're actually trying to find. So the distance here from P1 to the point, let's call this d, meaning the distance that we're after. We're trying to find a formula for that distance. And our normal vector can be graphed so that it's in that same direction, right? We're just going to slide our normal vector over here. So it might be easier to visualize this next bit if we go ahead and create a right triangle here. And let's think about a projection. So we're going to project the vector b onto the vector n, which means that we're going to have or visualize kind of a light coming in this direction, which is shining on top of b. So our distance that we're looking for is the same as the magnitude of the projection vector from projecting vector b onto vector n. And as a reminder, the magnitude of that projection vector is the component of b onto n. And since that component can be a positive or a negative value, we're going to wrap that up in absolute value bars to ensure that we're getting a positive distance. And as for the formula for the component of b onto n, that was the dot product of n dot b and divide that by the magnitude of n. Now I'm going to go double mag bars because we're going to be looking at magnitude bars and absolute value bars, which look the same. So now that we're incorporating both, I'm going to use single bars for absolute value and double bars for magnitude. This would be the formula for the component of b onto n, but we're going to wrap this numerator up in abs val bars, right? Because n dot b, this is a scalar quantity in here, and in order to ensure this scalar quantity is positive, we need to wrap it in absolute value bars. So to ensure that the component of b onto n is positive, we wrap that in abs val bars, which really means wrapping this dot product in abs val bars. So now let's go ahead and make this calculation. The dot product of our b vector with our n vector is going to be a times x1 minus x naught plus b times y1 minus y naught plus c times z1 minus z naught. And the magnitude of our vector n is going to be the square root of a squared plus b squared plus c squared. So let's put these in our formula. Actually, let's say this is just going to be that dot product, not quite d yet, n dot b. And then so now we'll put all of that together to say we're looking for the absolute value of, let's actually in this step also distribute a, b, and c into these parens. So we'll have absolute value in the top of a times x1 minus a times x naught plus b times y1 minus b times y naught plus c times z1 minus c times z naught. And all of that is enclosed in absolute value bars in the top. Now, this is the magnitude of n in the bottom, so we also are looking at a principal square root here, so there's no need for additional absolute value bars in the denominator here. Let's work with this a little bit because this isn't quite our desired distance formula. So in the numerator, let's gather our variables x1, y1, z1 together because truly these are our only changing quantities, right? This is any point and we're looking for the distance between any point and our given plane. So these are the things that are changing, and this formula should work no matter what point it is that we are considering. So our plane being given means that a, b, and c values are constant, and a point that we selected in the plane is going to be a constant value. So these can be considered constants, whereas these values will be considered our changing quantities. So let's get our variables together here. We're going to say ax1 plus by1 plus cz1, and then factor out a negative out of all of these constant quantities so that we have ax naught plus by naught plus cz naught, all having that negative factored out, and then close abs val bars, and then still divided by that magnitude of the normal vector. Now let's recall the original formula for our plane was ax plus by plus cz plus d is equal to 0. And any ordered triple x, y, and z that are in the plane are going to satisfy this equation. And so we actually chose an ordered triple in the plane that was x naught, y naught, z naught. Those values were in the plane, plus d is equal to 0. So since our ordered triple has to satisfy this equation, we can solve for d and get all of these values negative on the other side, but let's factor that negative out. And that gives us the same quantity that we see in our formula. So the value d from the plane equation can be used instead of this negative parens ax naught, by naught, cz naught. So we're going to substitute d in for that quantity in our derivation here. So all of this is the same thing as d. So our distance formula then becomes absolute value of a times x1 plus b times y1 plus c times z1 plus the value d from our plane equation, and that's all wrapped up in absolute value bars, which would then be divided by a squared plus b squared plus c squared, and this is the formula for the distance between an ordered triple, our point, which was x1, y1, z1, and a plane which was given by the equation ax plus by plus cz plus d is equal to 0.